Welcome to Draw the Logic, where we make complex ideas visual. In this video we will build a complete, ground-up understanding of how large language models actually work, from raw internet text, through training, alignment, and all the way to how they generate answers. The single most important thing to understand about LLMs is this: they predict the next token. That is the entire training objective. Everything else, the attention, the alignment, the reasoning, exists to make that prediction better. Given the cat sat on the model assigns a probability to every word in its vocabulary and picks the most likely next token. Matt gets the highest probability. The model picks it, appends it, and repeats that loop billions of times over billions of training examples. Builds the capability we observe. The full LLM pipeline has 7 stages. Collect data, clean it, tokenize it, pre-train on next token prediction, align with human preferences, deploy efficiently, and finally generate output. Every single stage matters. Better data and better training usually deliver more gains than any architectural improvement. An LLM can only learn from text it has seen. The training corpus is the foundation of everything. The main sources are the web via Common Crawl, books, academic papers, code repositories, and curated instruction following datasets. Modern corpora contain hundreds of billions to trillions of tokens. How much of each source to include is a critical engineering decision. Raw internet text is noisy. Before training, it must be carefully filtered. 5 key cleaning steps: deduplication, heuristic filters, language detection, classifier-based quality scoring, and removal of personal or harmful content. The result is a high-quality corpus ready for tokenization. Over-filtering removes valuable diversity. Under-filtering injects noise. Getting this balance right is hard. Neural networks work with numbers, not text. Tokenization converts characters into integer IDs the model can process. There are 3 dominant families. BPE iteratively merges the most common character pairs, used by GPT and Llama. WordPiece merges by likelihood, used by BERT. SentencePiece treats the raw byte stream, used in multilingual models. Here is BPE on the word lower. Start from individual characters. Merge the most common pair. L and O become low. Then low and W become low. Final tokens. Low and each maps to a unique integer ID. Each integer token ID is mapped to a dense vector, a list of hundreds of floating point numbers. These vectors are called embeddings. The embedding table has 1 row per vocabulary token. Looking up a token ID returns its embedding vector, typically 512 to 4096 numbers. In this vector space, similar words cluster near each other. King and queen are close. Cat and dog are close. Paris and Rome share a regional cluster. The geometry encodes semantic relationships. The famous result: king minus man plus woman equals queen. Relationships are encoded as directions in this space. Pre-training is where the model acquires general language ability. The objective is brutally simple. Given all previous tokens, predict the next one. Here is a training example. The cat sat on the ____. The training objective is to minimize cross-entropy loss. The log probability of the correct next token summed across every position. Modern pre-training runs use 1 to 15 trillion tokens, taking weeks or months on thousands of GPUs. Loss drops predictably as scale increases. This is the scaling law. The transformer replaced recurrent networks with self-attention. The key insight: every token can look directly at every other token in a single operation. No sequential bottleneck. In the transformer, every token attends to every other token directly, in one parallel operation. There is no sequential bottleneck. A word at position 1 can directly influence a word at position 500. Attention is built from 3 linear projections of each token, query, key, and value. The formula. Compute dot products between Q and K to get similarity scores. Scale by the square root of dk to prevent saturation. Apply softmax to get attention weights. Then blend the values by those weights. Let us unpack each part of the formula. Instead of one attention operation, the transformer runs H in parallel, called heads. Each head learns different relationships. One for grammar, one for pronoun references, one for long-range semantics. All head outputs are concatenated, then projected back to D_model. Total compute equals one single head operation. Each head just uses D_model divided by H dimensions. A unique position vector is added to each embedding. The original transformer used fixed sinusoidal curves. Modern models prefer rope, rotary position embedding, which encodes relative positions as rotations and generalizes well beyond the training context. Window. A single transformer block stacks attention and a feed-forward network, each wrapped in a residual connection and layer normalization. Here is one complete transformer block. The feed-forward network expands each token to 4 times D_model, applies a non-linearity, then projects back. Residual connections let gradients skip sublayers. Layer normalization keeps activation stable across dozens of stacked blocks. The transformer has 3 main architectural variants, each suited to different tasks. Most modern chat models, GPT, Claude, Llama, are decoder only. BERT-style encoders dominate retrieval and classification. Encoder-decoder models excel at translation and summarization. A pre-trained model can complete text, but it is not a helpful assistant. Post-training shapes its behavior. The first step is supervised fine-tuning. The base model rambles. After supervised fine-tuning on thousands of human-written instruction response pairs, the model gives clear, helpful, on-topic answers. SFT uses the same next token loss, but applied only to the response part of curated prompt response pairs. The result follows instructions, but still needs alignment with human preferences. SFT alone is not enough. Alignment methods shape the model's preferences, making it helpful, harmless, and honest. RLHF. Humans compare 2 model outputs. A reward model learns those preferences. Then PPO, proximal policy optimization, updates the LLM to maximize reward. Effective, but memory heavy. It runs 4 models at once. DPO removes the reward model entirely. Given preferred versus rejected response pairs, it directly updates the policy to prefer the chosen output. Much simpler and cheaper. GRPO generates a group of responses, rewards each one, and uses the difference from the group mean as the training signal. It eliminates the critic model, saving significant memory, used by DeepSeek R1. Most models generate a response immediately. Newer systems spend additional compute at inference time, thinking before committing to an answer. With test time compute, the model generates intermediate reasoning, checks its work, searches for missing context, and revises before giving a final answer. This is chain of thought reasoning taken to the extreme. During inference, the model generates 1 token at a time. Each new token is fed back as input for the next step. Token 2, Sky. Without a KV cache, attention must recompute keys and values for every previous token at every step. Quadratic cost per token. The KV cache stores those results, so only the new token needs fresh computation. The model produces a probability distribution over every token in the vocabulary. The decoding strategy decides which token to actually pick. Here is a typical probability distribution over the next token. Greedy always picks Matt. The highest bar. Temperature reshapes the distribution. Top K restricts sampling to the top K options. Top P. Nucleus sampling. Takes the smallest set of tokens whose cumulative probability exceeds the threshold P. Serving a large model at scale is expensive. Several techniques reduce compute, memory, and latency. Transformers are powerful, but researchers have found two important extensions: state space models for long sequences, and mixture of experts for scale. State space models maintain a compact hidden state vector and update it at each token position. Mamba adds a selective gate. The model can choose which information to keep and which to discard. Mixture of experts replaces the dense feed-forward block with many expert networks. A router picks the top two for each token. The rest are idle. You get a huge total parameter count while paying compute for only a fraction. LLMs are impressive, but they have serious, well-documented limitations that every user should understand. 5 critical limitations: hallucination, confident falsehoods, bias, inherited from data, robustness failures, privacy risks from memorization, and reward hacking during alignment. The safest attitude: treat every LLM output as a first draft. For high-stakes decisions, always verify, retrieve, or involve a human. An LLM is not magic. It is a carefully engineered system that turns large amounts of text into a probability engine, then shapes that engine with architecture, alignment, and decoding rules. The most important idea remains simple. LLMs predict tokens. Everything else is there to make that prediction more useful, safer, and cheaper. If this video gave you a clearer picture of how LLMs actually work, please like it, share it with anyone studying AI, and subscribe to Draw the Logic for more visual deep dives every week. Thank you for watching.